Continuing on with our unsaturated hydrocarbons, we're going to pick up with alkene reactions, which are very similar to alkyne reactions. They're just done twice. We have two major classes of reactions. They are addition and redox. Now, redox and addition do not have to be mutually exclusive. Redox we talked about earlier, where we add oxygen and produce carbon dioxide and water in a complete combustion reaction. But the simplest understanding of oxidation and reduction, oxidation would be the addition of oxygen or removal of hydrogen, and reduction can be the opposite of that, the addition of hydrogen or the removal of oxygen. So those two definitions for redox in organic compounds are the most simplistic version. In Gen Chem, you probably talked about oxidation numbers and all of that. We're not going to go into assigning oxidation numbers and looking at oxidation states, but these two general forms of the characteristics should get you through the amount of redox that we're talking about here. So if we're adding hydrogen, then we're having an addition reaction and a redox reaction. They are not mutually exclusive. So let's go. The general reaction for an alkene when we have addition. So we have our double bond here, and I can put the highlighter in there. This is our double bond. We're going to react across the double bond. So if AQ is our reaction, A adds to one side of the double bond and Q adds to the other. But we're going to take a look at some reactions where should A add here and Q add here? Well, let's find out. So some small molecule, AQ, is going to react with the pi electrons of the double bond. AQ can be water, chlorine, bromine, hydrogen, and we'll see some other reactions as well, like hydrochloric acid, HCl, and maybe even potentially HBr. The pi bond in this bond here, remember we have one sigma and one pi bond. The pi bond is going to break and its electrons are going to be used to bond to the pieces of AQ. The double bond always becomes a single bond, but that's going to always be the case. What happens is, and how it happens is going to be a little bit different with each version of AQ that we have, and some of them are going to require a catalyst for the reaction to go forward. These are some of the particular reactions we can see with alkenes. So here we have hydrochloric acid reacting, hydrogen goes to one side, chlorine goes to the other, and we end up with a hydrochlorination, is what it's called. With water, we can think of this as HOH. H goes to one side, OH goes to the other, and we end up with a hydration. We're forming an alcohol. Removing a double bond and adding water across the double bond. Bromination, we have Br, it's a symmetrical, so these are symmetrical. Addition, so we have one Br going to either side, here, and then down here with hydrogen, we also have a symmetrical addition. We have hydrogenation, hydrogen going to both sides, forming a single bond. Symmetrical reagents. So when we add hydrogen and bromine and chlorine, we may or may not need a catalyst depending on what's reacting. Hydrogen does need a catalyst. So hydrogen is a small molecule and it's going to need a catalyst to undergo the reaction. And I'll talk more about this in just a few seconds. Bromine, chlorine, we're going to see these in the symmetrical addition area as well. They don't necessarily need a catalyst. They're going to react, actually, that's one of the key components, is they do react without a catalyst. So if we're in lab, we can actually use the addition of bromine to tell whether we have a saturated or unsaturated hydrocarbon. Our unsymmetrical reagents like hydrochloric acid and hydrobromic acid, these are strong acids already, so they're not going to really require a catalyst, but adding water will require a catalyst. It'll require a strong acid like sulfuric acid or phosphoric acid. Well, phosphoric is kind of on the higher side, but not necessarily one of the 7 strong acids you might have memorized. But we can also put H plus above the arrow to denote that, or H3O plus, which is, acidic water, just showing that we need an acid there. One important part of alkenes is they are one of the things that help us make polymers. So when they add to themselves, they can build out in both directions, causing polymerization to occur, and we can add hundreds or thousands of these together to create different polymers like we see in our everyday world. Most of our alkene addition reactions are exothermic. Hydrogens are going to attach to each end of the double bond here in hydrogenation, but just because they're exothermic, meaning that they're going to give off heat, does not mean that they are going to be happening quickly. So generally when we have an exothermic reaction, that means it's spontaneous, meaning it will happen on its own, but just because something happens on its own does not mean it happens quickly. So we'll have to add a catalyst to make it go faster. So when we require a catalyst, it depends on what we want to do, what catalyst we'll use. So if we use a transition metal catalyst like palladium, platinum, or nickel, this is going to help us with the addition. It's going to make it go faster by using this transition metal in a certain way. I have a couple slides in a second that are going to show us how that's done. But in the grand scheme of things, what's happening here is this double bond is going to become a single bond, and we are saturating. So we're saturating this unsaturated hydrocarbon. So what we're going to do is add hydrogen across the double bond, and we end up with single bonds in the end. So no matter what we do, here we start with our trans, 1, 2, 3, 4. This is, I actually have it in there, transbutene. And over on the other side, we have cis-butene, but both of them, no matter what we start with, we're going to come across having butane as the product when we add hydrogen. So going this way will give us butane, or going this way will give us butane. Now notice this has a higher pressure because normal atmospheric pressures are around 1 atmosphere, 25 degrees Celsius. We've warmed it up a little bit, and we're using a transition metal catalyst. The thing about transition metal catalysts is they are not specific in that they will take any double bond and reduce it down to a single bond. So it will add hydrogen across any double bond. It's not going to be specific. So how does this occur? So it occurs in a few steps. Here okay, there we are. So step 1, we have the hydrogen molecule is going to react with the metal catalyst. So if this is the metal catalyst surface here, this blue area, the hydrogen atom reacts with that metal surface and it breaks the sigma bond that was between the hydrogen atoms. Because remember, the hydrogen atoms are diatomic, they're connected to each other. So it's going to break this and they're going to come down here and attach to the metal surface. But when it attaches to the metal surface, it's creating weak hydrogen metal bonds. So these bonds are not very strong. They're more of an attraction. Then the pi bond of the alkene is going to connect with the metal catalyst. The pi bond is broken, and a weak carbon metal bond, so a very weak carbon metal bond, is going to form. These weakly bound hydrogens are going to transfer one at a time from the catalyst surface over to the carbon. And then, so we have that happen twice. We're going to transfer over to the carbon, and that releases from the surface. And now we have a saturated alkane. Now this might not be important for this class, but depending on where you guys are going after this. So this can happen, so it's a little above and beyond. So because the hydrogen atoms are bound to this particular metal surface here, they're going to normally approach from the same side or the same face of the molecule, and that's called a syn addition. If they were to approach from opposite sides, so this means this, oh, go back. This is the same side. But if they were to approach from opposite sides, the reaction is called the anti-addition. So you can actually have a syn and an anti-product depending on, not in this case, but depending on the molecule. And remember, if I said you're taking this further, you're going to go into some type of research or something like that. Or if you're going to be doing organic synthesis, it's important to understand that we have different directions and different products that can form, because sometimes we'll have a front side attack, sometimes we'll have a back side attack, and it might be important. Now, the most likely way to get an anti-product from this type of addition is through isomerization. And so that double bond isomerization that happens, if it occurs faster than the second hydrogen can add, then you would get the anti-product. Now, again, that is above and beyond the scope of what we're going to be talking about. When we add halogens to a pi bond system, this reaction is going to happen through a trans addition, which results in a trans product. So one is going to go here, one is going to go there. However, it's a single bond and it's free to rotate, so we're going to see just the one product that's going to be freely rotating. So what is going to happen here is the bromines are going to break apart. We're going to get a bromine here, and this is going to be a single bond instead of a double bond. So we end up with 2-butene goes to, well, what do we have? 1, 2, 3, 4. So we have a butane now. And we have 2 bromos. 1, 2, 3. We have 2, 3 dibromo. So our product would be 2,3-dibromobutane. Here, same thing. Doesn't matter if it's a ring or not. We're going to get a bromine here, and no double bond. So we're going to end up with 1, 2 dibromo. Let's see, we start with cyclohexene and bromine, and we end up with 1, 2 dibromo cyclohexane, right? I'm just seeing if you guys are going along with me. But it is a trans addition, so because this final product does have, okay, so this product has all single bonds. So it doesn't matter that it's a trans addition because it's going to be free to rotate. But this molecule still has restricted rotation. So we're going to end up with a trans product because it's a trans addition. So trans 1, 2 dibromo cyclohexane. So like I said, bromine is a qualitative test that we can use in the lab. If we add that to the presence of a carbon-carbon double bond, the bromine is a deep red color and dibromoalkanes are colorless. So if we add the bromine to a solution in the lab and it still has that deep red color or dark brown color, that means it must be a saturated hydrocarbon. But if it changes to colorless without the addition of that UV light or heat, then that means it must have been an unsaturated hydrocarbon to begin with. So here we have our double bond. What's going to happen? Predict the products. Chlorine's going to add across the double bond, and you have, these are exactly the same, right? This is just condensed even more, but we're going to have 1, 2 dichloropropane. So we end up with an alkane instead of an alkene. Now HX, so this is our unsymmetrical addition. We have HCl, HBr, HI, H2O. Sometimes an acid catalyst is required. Generally, when one of the things that's being added is not already a strong acid, since HCl and HBr are already strong acids, we don't necessarily need to have an acid. So when HX adds across the double bond, you can get H on one side, so if we do it here, and X on the other, and again a single bond. Okay, I'm going to erase that. But who's to say the hydrogen should go there? What if the hydrogen goes here and the X goes here? So which way is it? We have 2 possible products. You should draw both possible products. We can have X go to the carbon on the terminal on the end, or we could have X go to the central carbon. We have two different possible products with two different names. So in this case, we're going to get what's called a major product and a minor product. How do you know which one will be the major product? This is going to be following what's known as Markovnikov's rule. So the addition of an unsymmetrical reagent to an alkene is going to be regioselective. In one direction, the bond formation or bond breaking is preferred to all the others. And actually, Markovnikov's rule is pretty simple. If you just remember that the rich get richer, or them that has gets, are two of the sayings that I have learned over the years. But the hydrogen adds to the less substituted carbon. That's really wordy, right? The hydrogen goes to the carbon that has more hydrogens to start with. And the X goes to the more substituted carbon, or the carbon that has the least hydrogens on it. So here we have, if we put HCl here, which one is going to get the hydrogen? Hydrogen goes to the carbon that has the more hydrogens to start with. So it's going to go to carbon number 1, and chlorine will go to carbon number 2 because it has less hydrogens. So that's going to be our major product. And our minor product will be the opposite, where the chlorine goes to carbon number 1 and the hydrogen goes to carbon number 2. Now this says not formed in your textbook. I don't like that because, you know, sometimes it is formed in a small amount, or it's just not in a great amount. So we have a major product and a minor product. I do want you to be able to draw both of them and then label them major and minor. Now, what I'm going to show you next is how this happens, but you do not have to draw mechanisms out for me. This is just for your own benefit if you don't like memorizing things. So how this happens is these electrons in the double bond, in the pi bond, excuse me, are more reactive than our other, than our other electrons have been so far. So these electrons are going to reach out and grab this H plus ion. Where did this H plus ion come from? It came from the acid. Because remember, acids dissociate in water. Actually, they ionize in water or in solution. So we'll say they are going to be floating around as little H plus ions, right? So these pi electrons reach out and they grab this hydrogen. They're going to break this bond, forming a single bond, and the hydrogen goes to one side of it. The hydrogen went to one side, and what in the heck is this right here? This is called a carbocation. This is not something carbon likes to do. Carbon is electron deficient here. Being electron deficient is not carbon's big thing, so it would prefer to have 4 bonds all the time. But if it can, it gets by with a little help from its friends, so it can kind of spread this positive out a little bit, and it handles it better if it has more neighbors. So the more carbon neighbors the carbocation has, the easier it is to handle that positive sign. So this carbon has 2 carbon neighbors, so it's a secondary carbocation. The reason why the hydrogen goes to the carbon that has more hydrogens is because if it has more hydrogens, like this one would be a primary carbocation, so it would less likely, it's going to be harder for it to handle having that carbocation intermediate. This doesn't stick around very long. It sees this chlorine in solution, if it came from the acid maybe, or it had another acid in solution. But if we're thinking that this is hydrochloric acid, this chloride is coming along, it's going to see that positive charge and it's going to be attracted to it where it can react. So the secondary carbocation reacts with the chloride that's in the solution and it forms the product 2-chlorobutane. Carbocations are going to range in stability. A primary carbocation, one that only has one other carbon neighbor, is going to be the least stable. This is a secondary carbocation. It has 1, 2 carbon neighbors, and this is a 1, 2, 3 tertiary carbocation. This is the most stable. You can have a quaternary carbon, but you can't have a quaternary carbocation because we have to have something missing in order for it to be a carbocation. So the more substituted the carbocation is, the more stable it will be. Like I said, it gets by with a little help from its friends. Carbon does not like being electron deficient, having that positive charge. So the substituted carbocation shares the positive charge with its neighbors, causing it to be just a little bit more stable. So when the hydrogen goes into the carbon with more hydrogen atoms, it's actually producing a more substituted or more stable carbocation. That's why Markovnikov's rule works. So let's practice a little bit of this. Let's find the major and minor products for this reaction. We have our HCl. The pi electrons are going to come out. Remember, this is actually H plus and Cl minus in solution. So these are going to come out and react with our hydrogen. Where does the hydrogen go? It's going to go here. Then that means the carbocation will form here because this bond broke, and we're going to react here. So our products will be this one and this one. Which is major and which is minor? If you said this is your minor product and this is your major product, you are right. The hydrogen goes to the carbon that has more hydrogens to begin with. So let's do some practice. Predict the products of the following reaction, give all products, and label the products major and minor if applicable. Okay, applicable? Yeah, you got it. Sometimes I say some things and it just doesn't sound right in a recording. Tomato, tomato. Okay, so here we have HBr. Similarly, this is a strong acid, so it really is H plus and Br minus. These electrons are going to reach out and grab that hydrogen. Where is it going to go? Now I move this to a line structure because I want you to see this is a CH what and this is a CH what. This one is just CH and this one is CH2 because everybody has 4 bonds. So this one's going to go here and the bromine, sorry I forgot the minus sign there, is going to go to the center. So we end up with these two products. I want you to name them, and I want you to tell me which is major and which is minor. Minor would be the bromine going to the terminal carbon, and major would be the central. Actually, I want to go back because I want to name these products. So let's name this stuff. We've gotten away from that for a few seconds here. Thought I erased that, sorry. So here we have 1, 2, 3. We have propene. You don't need to write the 1 because no matter where I put it, it's going to be 1 propene. You don't need a number till there are 4 carbons. So here we would have 1, 2, 3. We have 1 bromo propane is our minor. And here we have 1, 2, 3. We have 2 bromo propane as our major. I want you to practice this one. Predict the products of the following reaction. Give all products. Label the products major and minor if applicable. You need to please pause it and try it. So what is going to happen here? These electrons, remember this is hydrogen, ion, and bromide. These electrons are going to come out and grab this hydrogen. And where is the carbocation going to go? 1, 2, 3, 4. That breaks, it'll be 3. So we're going to have our positive carbocation and our hydrogen is going to add here because this is going to break. The bromide is then going to come back and add here for our major product. So 3-methyl-2-pentene has a possibility of forming these two products, which are 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We have 3-bromo, 3-methylpentane, and we have 2-bromo, 3-methylpentane. Which is major, which is minor? Our major is going to be, oh, go back. I didn't write it in there. Darn. All right, so which one is our major going to be? We said the one that the bromine goes here. So this is our major, and this is our minor product. All right, good. So when we add water, it's going to be just a little bit different. Not too much, just a little bit, because we have an acid catalyst. So this hydrogen is actually from the catalyst, not from the water that we're adding. Remember HOH. These double bond electrons come out and they grab the hydrogen that's in the solution, and the hydrogen is going to go here. So we end up with a methyl, and we form this carbocation, which is a tertiary carbocation. Now we have our water that's in solution as well. So water is here. Water has these partial negatives here for those electrons, and it has a partial positive on the hydrogen. If you remember, that's a dipole. It's a dipole. And those electrons are going to be attracted to that carbocation. So now we're going to form a bond here between the oxygen, and the hydrogens are still there. And this is a problem because oxygen doesn't want to be a carbocation even more than carbon, if you can believe it, because oxygen is a highly electronegative element, having an electronegativity of about 3.5. So it does not want to have those a positive charge. It would much prefer to have a negative charge. So what's going to happen here is the hydrogen is going to donate its electrons back to the oxygen, and it's going to leave. Then it's reforming this hydrogen ion, which doesn't have the electron. It's going away and reforming the catalyst. Because catalysts can't be destroyed in the reaction, right? They have to be a part of it. So then when we add water, we're going to end up reforming that catalyst. So how do we add water? Well, we're going to hydrate this in a simplistic way without making you go too far in depth into this. So we're going to add it just like we did before. Think about it as HOH. With that catalyst, the hydrogen is going to go to one side and the OH to the other. But which one is it? You're going to follow Markovnikov's rule, just like we did before. So the hydrogen is actually going to go preferentially to our other side, and the water, the OH. So the hydrogen will prefer to go here, and the OH will prefer to go here. So we have two possible products here. This would be our major product, and this would be our minor product. And their names are, let's see what this one was. This was propene again, and we end up with 1, 2, 3, 1, 2, 3, 1 propanol, and this would be 2 propanol. And don't worry about naming those products just yet. So this is called hydration. I want you to practice this. Predict all the products that are possible for this reaction, and if necessary, label them major and minor. Pause it. So this is one possibility. This is one possibility. This is our major, and this is our minor. And we don't have to worry about naming the products yet, but we can name this 1, 2, 3, 4, 5. We have an ethyl, and we have a methyl. So this would be 2 ethyl, 4 methyl, 1 pentene, and these would end up ending in all because these are alcohols, so we don't have to name those quite yet. All right, where are we? This is just a reminder that a methyl, then we have a primary, secondary, and tertiary carbocation, and the stability of the carbocation is going to increase the more neighbors it has, the more carbon neighbors it has. The last reaction we want to talk about is polymerization. A polymer is any long chain molecule that's made by many monomers. This is our monomer in this case. It's an alkene. And it's the single part that's going to end up repeating. And it can build out from both sides, which makes it a very effective way to polymerize. So when you see a polymer reaction, you might see something like this. This is the repeating unit. It repeats n number of times, and it's going to continue to grow in both directions. So we show the structure of a polymer by placing the parentheses around the repeating monomer unit, and we say it repeats n number of times. That n is the subscript, and it indicates that's how many times it repeats. Now, the structure of polymer chains can be reduced by repeating the enclosed structure in both directions, and this is actually just a following. This is tripping over my words in this recording. This is from polypropylene, which is polypropene. So we have actually, this is our repeating unit here. And when it polymerizes, propene becomes many propenes. And you might actually see this also known as polypropylene. So does this matter to you? Do you use any of these? Yes, you probably do. So let's just name a couple of them here. Styrofoam has a double bond, and it actually differentiates between alkanes and alkenes, and it helps in styrofoam production. And what happens is it contributes to forming some foamy but light texture to the styrofoam. And so what the molecule here is called styrene. Okay, that's what we're looking at. And it has the connection between the atoms. They're more loose, and that's what gives it that airy and light texture. But it's also flammable, so be careful with it. One other one that you probably use daily, and you should kind of be careful with sometimes, is tetrafluoroethylene, because that one is also the Teflon coating and nonstick coatings. What happens is it has a polytetrafluoroethylene coating, and it helps prevent the Teflon from getting burned. So when you're heating up your pans and you forget about them on the stove, you're actually damaging the coating to the point where it starts to peel off. And I'm not going to give you the studies on that, but once your Teflon and your coatings start peeling off and going into your food, definitely replace your pans because you don't want to be eating this molecule. It doesn't damage the steel but as quickly, but it does help preserve the Teflon for longer if it's getting overheated. You use a lot of these most likely, break-resistant containers, PVC piping, construction tubing, different types of polymer examples here for you to take a look at. Moving on to alkyne reactions. Alkyne reactions are the same ones that alkenes undergo. They just do it twice instead of once. So when they react, we're going to follow Markovnikov's rule one at a time. We react here. The hydrogen goes to the one with more hydrogens. This doesn't have any hydrogens. So we get our X here and our hydrogen on the terminal. And the second reaction follows it as well. Since there's still no hydrogen on that carbon, it's going to get both of our X's. So we add it twice. Let's practice. Pause it, practice, see what you can do, okay? And remember that this molecule, I drew it in PowerPoint, so it could have been like this. 1, 2, 3, 4. 1, 2, 3, 4. So be able to see it both ways, that this linear structure, it is what we might actually typically see. I just had a harder time doing that in PowerPoint where it looked cohesive. All right, so our first reaction, where's the hydrogen going to go? Terminal, carbon number 1, or carbon number 2? You have to ask yourself that. And our first reaction is going to give us this as our two possible reactions. Which one's major? And then finally, we get our second addition where we get this product. You can just take the major product and move it forward at this point. If you were to have the minor of the minor product, you're going to have such little of that product. It's not going to be enough to mention. So if you just want to show the major product on this one, that's probably fine. All right, try again. So practice and try again. Actually, I drew that incorrectly. I was trying to show you what it would look like without having it there, but I think I'm just wasting your time, so I'm just going to keep going. All right, 2Cl2, where are they going to go? One goes to one side, one goes to the other. We break one of the bonds and we get this. Then we do it again, and we end up with 4 chlorines on our final molecule instead of just 2, like we would see in an alkene reaction.